So today's class is an extension of what we have learnt in our previous session. Okay, no need of any laptops as of now. Okay, so we are going to see how do we actually build an attention mechanism using an LSTM. Alright, so the last class, from where I have begun, you were at RNN. You just started with sequential data, okay? You were at RNN. I started with what? Long short term memory. Yes or no? Right. So what for is a LSTM used? LSTM is used to overcome the limitations of RNN. What were the limitations of RNN? Vanishing gradient descent. Because of that, what was happening? It could not retain longer sequences and predict correct output, right? So it was called as a short-term memory, right? It had only one output called hidden state that you were working with to calculate the next out. To calculate the output of your model, right? Now, what happened? Then came into existence LSTM to overcome these limitations. What is the full form of LSTM? That means what? Apart from hidden state, you also had a cell state that was trying to give the long-term memory to your model. Was it complete long-term memory? What was it? Some important words that were relevant to the context were stored onto the cell state in order to predict the output. Okay. Now, then I explained you about sequence to sequence model. So, sequence to sequence model, what is going to happen? It is just not one side of the model. Now, it is all about two-sided model. Two-sided model means what? Suppose you have got an input sequence coming. Like I gave you an example also of about language translation. So, if I am giving my input as, hi, I am Priyanka, the output should come as, say it is a Hindi translation, Namaste, main Priyanka hoon. Correct? So, this input, hi, I am Priyanka, in a sequence to sequence model. What does a sequence to sequence model hold, by the way? What is it consisting of? One side it will have encoder, the other side decoder, right? So, the input, hi, I am Priyanka, will be taken by the encoder model. That is also an NN model, neural network model. It could be an RNN, it could be an LSTM, it could be a GRU, depending on what is your application, okay. Now, it will take that particular input, it will convert that into a context vector. This is important. Sequence to sequence model, how it is different? Encoder will take up input sequence, compress the entire information in that input sequence into one context vector. Then at the other end, this context vector will be utilized by whom? By the decoder. It will be taken as an input of a decoder and then it will give me a processed output sequence. Are you clear? So, at the encoder end, I am giving input, hi, I am Priyanka. It is going to understand what exactly it is, map all key to values, map all, vectors together, process on it, come to a context of it, that this is in language in English telling, hi, I am Priyanka, I am supposed to pass this on to decoder now. So, now the decoder, what it is supposed to do, it will take that compressed vector, which holds that information of that input sequence, performs some processing over that and gives you an output translated, Namaste, main Priyanka hoon. So, are you understanding how this encoder and decoder thing is working in a sequence to sequence model? Now, after that, I taught you there were some disadvantages in that sequence to sequence model. What was it? See, if you give a very large corpus as an input to that particular encoder, to convert that, compress it into one context vector, it will be very, very difficult. It will not be able to do a proper justice to your output. Are you clear? Secondary, I told encoder is again a neural network, sequential neural network which handles sequential data, So, it should be either RNN or LSTM or GRU, but of course, yes, RNN if it is, of course there will be vanishing gradient descent problem. You cannot use longer sentences. But again LSTM has got its own limitations. If at all you are working with a real-time data where you have very, very large size of your sequential data that you are giving, LSTM also will not give you proper accuracy. One more problem is a bottleneck issue. You have to keep on, calculating your hidden states every time. LSTM also, if you are taking, it works sequentially to calculate your hidden state. So as your size of input grows, imagine how much time it will take to get your output. So there was this need to break this sequentiality in the taking of the input and add some parallelism to it. To add some concurrency to our process, we introduced attention mechanism in my previous class, right? You remember I gave you one example also. When I put a slide onto the screen and you are not concentrating, then if I make you get up, you do not have at that time, at that spur of a moment, you cannot go through entire lines what I have been printed over there. You'll just go through some highlighted words that catches your attention, and then you'll be able to predict something or the other as the output. Yes or no? Some relevant output. So in the same way also attention mechanism works. You are not able to process sequentiality in taking the input. You will check which next input is important so that I can use it to predict my output. Are you clear? So that is nothing but an attention mechanism in a very, very layman language that I can explain it to you. Are you clear? Right? So the other day we saw attention mechanism. Do you remember the process? How did we calculate attention? See, there are, I again want to tell you that there are two types of major attentions: self-attention, cross-attention. Okay, in that again, if you first understand the process, you will understand various other types also. Okay, so what is this process that I am talking on? See, what you will do, you will always have a set of input sequence, a list of input sequences, right? Tokens that we call, correct? Yes or no? So, there is always a word that you would try to have as an input, a token that you will have as an input. You want what should be the next input that should have my attention as a machine. You are making the machine train. So say if I take the same example which I gave just now, hi, I am Priyanka. So in that, suppose here I am at I, and then my next attention should not go at am, it should go at Priyanka. So how does the machine understand that? That is done through attention mechanism. So suppose here I am talking on I. So I is the token or the word that I am trying for what next is supposed to be. What next? How similar, what is the correlation between this particular word called I with all the other words that are present. Now this I, the word that I am talking on, the current input that I am working on, is called as what? Query. Okay? Remember Q, K, V from my last class? Query, key and value. So this I that I am talking on, that I am focusing on right now, is my query. Now this I am supposed to find, correlate with every other sequence. Now here comes self-attention and cross-attention. I create a list of key. What is this key? If it belongs to the same input sequence, all the other words, it is self-attention. If it don't belong and belong to something else, it is cross-attention. Okay. So if key holds the list of words like again hi, comma I, comma am, comma Priyanka, for which I am querying through my current input sequence only, it is called as a self-attention. Clear enough, guys? Okay. So now query is I, key holds key holds all those four words from my sequence. Hi, I am Priyanka. Now this I, you are going to take up a suitable mathematical function, pass this query and also key, and try to figure out how they are related to each other. Are you clear? Okay. So there is this mathematical function which actually tries to figure out this attention score that we call. What is this attention score? It's like you are passing query and key through a mathematical function to see how well they are related to each other. Clear enough? Now attention score is like a logit, means it is a rough output value or a vector. You cannot See, what are you doing? You are taking this I, you are applying a mathematical function and calculating attention score of I with respect to high, with respect to again I, with respect to again am, with respect to again Priyanka. So you are calculating attention scores using self-attention for all these 4 keys that are present for this query. Now which one to pick up? All of them will give some rough results. Yes or no? So you require a proper distribution of that attention score. Mean for you or to machine to understand, it should be kept into probabilistic range. Means from 0 to 1. Suppose my attention score of high, my query is I, right? So I with high is 0.1 and high I with Priyanka is 0.9. You will clearly say that the next word the machine should move to is Priyanka. Yes or no? So, a rough logic will not work. You have to pass that through a suitable distribution function. What is the distribution function? Probabilistic function. And the best probabilistic function that you can use here is a softmax function. Please remember that. Okay. So now what you are going to do? You took the key, you had the query, then you applied some mathematical function. What could be the mathematical function? It could be an addition, it could be product, it could be a scaled dot product, etc., etc. Now based on this, you have defined various types of attention mechanisms. What are they? Additive attention mechanism, dot product attention mechanism, scaled dot product attention mechanism, etc. Are you clear? So you are clear now what is self-attention, what is cross-attention, what is additive attention, what is dot product attention, what is scaled dot product attention. To the dot product of key and query, you will be dividing it through square root of dimension of key. You can ask me why this scaling. This scaling is required because sometimes dot product of 2 elements that you are doing becomes very high. Your machine cannot work. There will be lot of time that will be consumed if the data is quite big. That is the reason you have to scale it down. So to scale it down, because you are doing it every time with key, you have to scale it down the result with dividing it with under root of dimension of key. How it will be done, we will see. So there are different types that I was telling. So once you get that attention score, okay, now does the machine directly work with these words? No. Machine works with now vectors. So you require vector also. So the vector to all these keys are actually the values that we call. So it is stored inside values. So it will now call upon the value, multiply each value with its attention score. Now suppose if I have high I am Priyanka, high ka probabilistic score, probabilistic attention score, what we call now is an attention weight. When you pass attention score through a probability distribution function, it is now becoming an attention weight. So now say high, because my query is I. High will not hold that much significance to it. So let's say the distribution is 0.01. Okay. Again I is again 0.02. Am again 0.00 something. And the remaining 0.9 is Priyanka. So now these all approximately 0 weights get multiplied with 0 with high, 0 almost 0. 0.0 is almost 0. So 0 multiplied with high, 0 multiplied with I, 0 multiplied with am. All added, 0.9 multiplied with Priyanka. Now this weighted sum will give you what? 0 with high ka vector, high value, some value, numerical value only. So 0 with some numerical value is 0. Yes or no? And then I multiplied with some value 0 because I ka probability is coming almost 0. Am probability is almost coming 0. Okay. Then Priyanka that I am giving. After I, what should be the attention going to? Priyanka. So that 0.9 is getting multiplied with the vector of Priyanka and the result is coming as vector of the next word that I am paying attention to. Are you clear? So that's how the next word is predicted. using attention mechanism. So what new you are adding? You are not moving sequentially. You are using attention weights to determine what next word you are supposed to jump on to. I hope I am clear enough. See, I cannot explain you in more simple sense this attention mechanism. You have to understand the process. See, what are you doing? You are taking a query to which you have a list of key. If the key belongs to the same input sequence, it is self-attention. Otherwise, it is cross-attention. So, the mechanism that I am choosing here to build our next exercise is self-attention. That's why I am emphasizing more on it. Okay. Now, you have a query, you have a key belonging to same input sequence, self-attention. You apply some mathematical operation on your query and key like a scaled dot product application, mathematical operation. If you are using that scaled dot product operation, now the attention is called as scaled dot product attention. Clear enough? After that, what you get is an attention score. Attention score of query with respect to every other word in the key. It is a rough logic. What you require is a proper probabilistic output. So pass that attention score through a distribution function. Here what you are going to use as a distribution function? Softmax. Okay. So once you take that softmax function, all the outputs will be in the form of probabilistic distribution. Multiply those probabilistic distributed weights now, attention weights that we call, with the values of every vector. You will get the answer as where your next attention word should go to. Clear enough with attention mechanism? So this is now a revision class actually what I am telling to you. We did not even start what we are going to do today. So if you are okay with attention, then only I will move ahead. How many of you are okay? Please raise your hand. Attention mechanism, simple process. I cannot see. So you want me to repeat this again? Yes? Okay. What did you not understand in attention? See, why are we going for attention is first importance. Okay. So if you have learned RNN and LSTM, you should know everything is calculated sequentially, one after another. But what is the problem? The problem is with larger sentences. Okay. The problem is with larger sentences. You cannot run it sequentially. Okay. Your efficiency will be decreased of a particular model. So what are we supposed to do? You are supposed to implement some concurrency in the model, wherein if I am talking on one word right now, my attention should grab to the next important word that is present in my input sequence. For that reason, we are using attention mechanism. Okay, right now you try to understand that attention mechanism process, how it is. How it is, whatever word you are standing right now at, that is your query. Q, that is your query. And all the remaining words that are present inside the sequence. Like I told you, if I am doing machine translation, I said I gave a sentence. Hi, I am Priyanka. That's what example that I am telling, right? So the output should actually come after translation as Namaste, main Priyanka hu. But first this processing should happen. What processing should happen? Hi, I am Priyanka. Suppose there's much more to it. The other sentences are also appended to it. Where to go after my query? Suppose right now I am standing at I. I am processing I. I am a machine, I am processing at I. Okay. So I is my query. What is it technically? It is my query. So now where next? Because now I am not running sequentially, right? I am grabbing some attention where to go to next. So for that reason, I is related to what best word inside your input sequence you are supposed to calculate. That is through attention mechanism. So I is your query. All the other words in that input sequence are your key. If you are trying to put all these words into a list called as key list, okay, so suppose key is there and then you are querying it, what are you supposed to find out? You are supposed to find out what significance this query hold with all the other words that are present in the key. So my key here is hi, I am Priyanka. I am right now processing I, so I is my query. So now we'll try to find out what importance does a key hold on this particular query. So we try to figure it out through some mathematical operation, wherein we apply a mathematical operation. Suppose here we are applying a dot product application. Okay, so dot product we are going to use scaled version, scaled dot product of key and query. Okay, right? So what does it give me? It will give me an attention score. I'll give you one simple example and you will understand this, but try to understand what I am telling. Okay, so this is query. I is now going to relate with hi, is now going to relate with I, is now going to relate with am, is now going to relate with whatever name that I have kept, I have given there Priyanka. Okay, fine. Now, that mathematical operation that we are using in our exercise is scaled dot product. Okay, so that will give me some answer. That we call it as attention score. So now attention score means if I am at a query I, what is the attention score of hi? What is the attention score of again I? What is the attention score of am and then of Priyanka? Means after I, what next word should grab my attention as a machine? Understanding? So now answer when you give to a dot product, you get as a rough value. Means you will not be able to see a machine if it has to take a decision whether it has to take that word or drop that word. It is like either 0 or 1. Yes or no? Either to go for that word next or to drop that word. So either 0 or 1. So now when I am doing this dot product normally, it's giving me rough figures. Machine will not be having anything relevant to 0 or 1. You will not be able to give some decision to that machine. So in order to give that decision to the machine, you have to give it in a probability range. Probability range is what? 0 to 1. So anything above 0.5 will be taken as 1. Anything below 0.5 will be taken as 0. So the machine will understand whether the next word is important or not. Yes or no? That is the reason once you do that dot product thing, when you get an attention score, it's very important you pass that through a softmax function. So once you pass that through a softmax function, distribution function it is, you get all the figures that you got converted into between the range of 0 to 1. Now the machine can very well figure it out whether which one is of highest significance out of it. Okay, now 0 to 1 may when you get that, machine will predict the next word. How it will predict? It's not like it is choosing one word. It is again taking that sequence only, multiplying weights of every other word with it. So hi was to be omitted, so that output of softmax for hi came as approximately 0. For I to I again 0, I to am say 0 approximately, and then I to Priyanka it came a good number, say around 0.9 for an example. So now what the machine will do, it will take up all these weights, do a linear transformation on it. So 0 multiplied with vector or value of hi, because it works with numbers. It cannot work directly with words, no. So value it is going to take 0 multiplied with value of hi, 0 multiplied with value of I, 0 multiplied with value of am, 0.9 multiplied with value of Priyanka. So you add all of them, multiply and add, what you will get? Linear transformation. Obviously you will get the vector which is relevant to Priyanka. So the machine predicted that the next word that it has to jump on is Priyanka and not am. So this is just a very small example that I have choosing, that machine has to jump onto what next word. What next word should grab its attention. For that reason, calculate attention score and calculate attention weights. Then apply linear transformation, get the next word where you have to pay attention. Okay, so this was about a recap of attention that I taught in previous class. Now, in today's class, we are trying to build a model using LSTM and attention mechanism. What type of attention mechanism? Mathematical operation wise, if I want to tell, I'll tell it is scale dot product attention. If I have to see it in terms of key, query and value, it is self attention, because all the keys will be developed through the same input sequence. Clear enough? Now, I was talking on scale dot product attention. quickly go through this. This is the formula for a scale dot product attention I have been talking on. It is a dot product of query and key. Key should be transformed, no? Dimensionality dot product, it should be matching. So that is the reason Q, K transform, scaling it with a under root dimension of key, because you want to normalize it so that it don't explode it in the range. Now, once you get this, you can see this part, QKT by root DK, it is nothing but attention score. If you want to get attention weight out of it, you have to multiply it with what? Its value, and also pass through, you have to pass it through your softmax function first and then get an attention weight and multiply it with its value. So overall what you will get is what is the next word that you have to pay attention to. Are you clear? So when you are designing this model, you have to make sure to your attention model what you are supposed to give inputs. You have to give key, query and value. Clear enough? Self-attention that I was talking on. Self-attention is a general concept where each word or token in a sequence attends to every other word in the same sequence. That is important. Okay? And then it computes attention weights using scale dot product attention, but specifically in a setting where you have query, key and value coming from the same input sequence. So if it is same input sequence, it is self-attention. Okay. Now, summary of what we have been working on till now. Scale dot product attention is a mathematical operation which is used within attention mechanism. Self-attention is a specific used case where attention is applied within same input sequence using scale dot product. So if I want to put it in a nutshell, scale dot product attention is the mechanism. Mechanism means the mathematical operation that you are using. And self-attention is how you are applying that attention, that mechanism. Using same input sequence or using some other sequence, Self-attention, for the same input sequence you will build a key. Cross-attention, for some other sentence you will build a key. Are you clear? Now, we'll see this example, you will understand it more better. What is this example sentence that I have taken over here? The cat sat on the mat. So, obviously, you'll have to do some pre-processing so that the machine understands the sentence. For that, the very first thing is tokenization. You'll pass it through a tokenizing function. It gives you all the token splitted words. The cat sat on the mat. Next is what? Creating embeddings out of it, assigning vectors. So, choose a suitable vector dimension, assign vectors to all of them. Okay, pass that through embedding. Now, here for ease, I have chosen 3-dimensional vectors. Okay, try to understand this problem, how attention is coming. So, the has got these vectors, 3-dimensional vectors till mat. Any random vectors I have taken. Now we are supposed to calculate the what? Attention score. How do you calculate attention score? Using mathematical operation. Here what we are using as mathematical operation? Dot product calculation. Okay. So you can see here, I am trying to calculate attention of cat. So what is my query? Cat. Query is cat. What will be key? The cat sat on the mat. All these words will be inside my key. But my query is cat. So after cat, what is the next word that holds more importance in that particular sentence? So I will try to calculate attention score of cat with respect to the, again cat, sat on the mat. Clear enough? So cat is my query, the is my key. I am calculating here dot product. You can see this is my answer. Okay. Now, I am using scale dot product mechanism. So, I am supposed to normalize this with under root dk. Dk is dimension of your key. How much is the dimension of your key? You have chosen as 3-dimensional vector, no? So here you are using it under root 3. So this is your final scaled attention score. So you got attention score. Like this you will calculate attention scores of cat with respect to cat, cat with respect to sat, cat with respect to on, cat with respect to the, cat with respect to mat. See the attention scores. First one is 0.1, next again 0.16, 0.27, 0.11, 0.11. Almost all of them are similar. You are not able to figure out which one is actually correct. So these are all rough logits. So in order to make them more, utilize it for better option, you will apply a probabilistic distribution function over it. What is that function? Softmax. Softmax ke liye you should first remember softmax formula. E power I, if that is your, I is your value that you are calculating softmax for, E power I by summation of E power I. That's the formula for softmax, mathematical formula that we are using here. So you see, these are all your attention scores that you want to form a distribution function of. So E power all these attention scores you will calculate and keep it. Sum of these exponentials you will calculate and keep it. Now you will take up each exponential score and divide with the sum. That will give you a probabilistic distribution. So you can see now everything is in the range of 0 to 1. So the holds attention weight 0.16, cat holds 0.17, sat holds 0.19, on 0.16, the 0.16, mat 0.16. So which one is holding more attention weight? 0.19 is for sat. So after cat, what is the next word that requires attention of the machine? Sat, indicating the strongest attention score. So this was just a very small sentence. It will work even better on a bigger sentence wherein you have large amount of key and then you just figure out attention score and attention weight and jump onto that particular word for predicting your output. Are you clear enough with attention now? This problem has sorted your doubts, right? Now we will move ahead. We will start with our code building. So my model today that I want to discuss is an auto-completion model. Auto-completion model is similar to what you have done previously with LSTM. We predicted next word. But here I am not predicting next word. I am trying to get some, a complete sentence. So sequence to sequence. Given certain sequence of words as a sentence, prediction is also a sentence which is a sequence of words. Mind it, I am not using encoder and decoder part, but then suitably a part of it, okay. But what I want to build here is how that sequence to sequence model is implemented using self-attention, using mechanism of scale dot product. Are you clear? So if you understand that part more in detail about this, encoder and decoder, how they are used in transformers, everything you will learn in transformers. If you understand this, this will make sure how you will use attention using LSTM, using any sequential model. Are you clear with that? Fine. Now, here we are using single-headed attention, means only one set of key, query and value. There will be some tasks which require multiple keys, queries and values. That is called as multi-headed attention. All those things you will see when you will learn transformers. Okay, right away it is single-headed attention only, means only one set of key, query and value. Self-attention we are taking, means key will be generated with the same input sequence, and mathematical operation we are choosing is scale dot product, so it is also a scale dot product attention. Are you clear? So this model will be using all of these things inside it. You are supposed to design it. So code overview I am bringing. First is obviously the data preparation. You will be importing libraries, loading the data sets. You will be cleaning your data set if at all you require, and then converting all these words into its input indexes or vectors as and then required by your machine. Then here you will see a new way of dealing with the data, that is all your input-output pairs will be generated through data loader. Okay, so you will use data loader here, and data loader setup we are going to see. Why data loader? Because today we will see how big is your input. You will see a complete book will be given as an input to it, how it is going to get the answer. So if there were very less number of sentences, need not use a data loader like how we have done in our previous exercises. But then when you are working with longer lines of code, then all of them has to be given as batches. So whenever you are working with batches, to avoid complicancy, you will be using data loader, because it helps with getting good output with respect to batches and shuffling of batches to get better generalization of your code. Yeah. Then you will use attention class here, scale.product attention class. You will implement this model of auto completion using LSTM. You will train this model and then test with the model. So this would be the entire sequence that I will be following to understand how an exercise we are going to build over auto completion model. So the first one that will require more of your attention is data preparation only, because the data is a text data that we are choosing here. So again I am reminding you one thing, in today's exercise you are using a text file. Tomorrow when you will do your hands-on, you will be using a CSV file. Okay, I am giving you that hint also. But then the processing remains the same. Okay, so when you are working here with the text data, machine cannot understand that text. Machine cannot understand that string. You have to get down or break down or prepare your data set in such a way that you come down to what? Input-output pair. X train, Y train, X test, Y test. Till that point you have to prepare your data set and then start feeding it to the model. So data preparation is a very big module that you will be writing. Now, for that the very first step, I am gonna import the libraries. So what all libraries that I am importing here? I am importing Torch, NN, because I am building neural network. I require optimizers inside my model, so Optim. Then I will be working with numerical calculations of using several arrays of vectors, so I am calling NumPy. And then I told you these three are like these, above four are like from the previous exercises that we have been doing. The remaining three this one you must be familiar with. sklearn.model selection, train, test, split. You have been using this a lot in your machine learning, yes or no? Yeah. What is it used for? Splitting your data into training and testing. Okay, so for that same reason here also we are using it. Now these two are little new to you. Okay, so what is this? Torch.utils.data.data loader, if I am taking. This particular import will help me to efficiently load the data and also convert the data into batches for efficient training purpose. Okay, that is the reason we are using data loader. Learn data loader properly, guys. It will be beneficial for you for later on exercises also. Okay, next is tensor data. So tensor data means what? Whatever x and y that you will be generating, that should be in the format of a tensor. Why do we require that? I explained you. Why your data set has to be converted into tensors before you give it to the model? For computational speed, for GPU acceleration, okay, for what else? For getting that portability onto your code. Okay, your code can run on any machine if it is in the dimensions of a tensor. Okay, now, next one is RE. RE is regular expressions module. Basically, I just imported it, but I have not incorporated that in exercise. You can. See, basically, when you are using tokenizing, when you want to find out a certain specific pattern related to a particular sequence, you will be using regular expressions. You might have seen that when you have learned Python. Okay, so that is regular expression module. I'll again explain you how does a data loader work. So data loader is going to wrap a particular data set and provide with efficient batching It will be splitting your data into multiple batches and then so that the machine can train better on smaller batches. It will be helpful for shuffling. Mind it, shuffling we will do for training of the data more, not for testing much. Okay, so for training data you will be doing a lot of shuffling because it results in efficient training, it results in better generalization of your model. Okay, next is parallel processing for faster data loading. You can parallelly work with large batches of data. Automatic iteration, because you are fixing all your data into, dividing that into batches. Iterations would be easier because data loader will be working directly with the batches. So it makes your task simpler. That is the reason of learning data loader. Why using tensor data set? That I told you, it helps you to organize your data whenever you are working with PyTorch model. It makes your data easy to batch, shuffle and sample. It will help you to streamline your training operation. Basically, in other words, you are converting your data set into first objects, into the objects, or if I want to say, it's like sampling your entire data into tensors. Okay, so you will see, as I explain you the code, you will understand where are we using this and why. Now RE, as I told you, for pattern matching, for text cleaning and for validation you can go for it, but here I have not used. There are again some inbuilt methods that are there in RE that will help you to do that. Okay, now beginning, load your data set. So here I am uploading an entire book of Alice in Wonderland. Okay, it is a text file that I am using here, and then I am reading this text file and storing it in a variable called data. So here I am using with, open, file path, R and encoding as file. The file will be closed automatically. It prevents the memory issue, and then here using an encoding called as UTF-8. What is this encoding? It is similar to like your ASCII encoding, but then this UTF, Unicode transforming format, here you are using this type of encoding to avoid errors that could happen with some special characters while you are reading your text data. There are a lot of special characters that are present in your text data, right? So to avoid any error into that, you will use this type of encoding. Okay, now once you have done that, you will read it and then transfer this entire content of the file into the variable called as data. So now let us see and review what are the first 1000 characters that are present in your text. So you can see it is like this. As I told, it is a novel actually, Alice in Wonderland. So this is my first 1000 characters that I have printed out of my data. It's not even the complete input that I am giving. These are just 1000 characters that are printed. So you are working with a bigger data set today. Okay, are you clear? So if you just take the entire input as data, and then what would be your next step to prepare this data? So the very first step that comes is tokenization. What does the tokenization operation do? Split the data into unique tokens. So now you can see here what I am doing here, basic text cleaning. I am defining simple tokenized function wherein it is taking parameter as my input data, and then what it is returning? What it is returning, guys? Data dot lower dot split. So what is the dot split function? Dot split function will break down that sequence into individual words wherever they are encountering space, and then automatically it will be converted into lower cases through that dot lower to avoid case sensitivity. Okay, so your input you will be now splitting into words, lower casing them and returning. First we will define a function, then we will apply that function. So I am applying now, what is it? To my data, I am applying this, I am calling this function on my data, and I am storing the result called as tokenized text. Clear enough? So now tokenized text will contain what? Will contain what? all the words that are present inside my data. Now, once you have got those words, you are supposed to generate index out of it. Okay, in my previous exercise, apart from index for input, I generated vectors also there and then. Yes or no? But then, here I am not doing because the corpus is too large. You will see vectors will be generated and given to the model in the later stages. Here I am not displaying you the vectors. What I am doing here is, I am creating a vocabulary by generating index of every word. Okay, so you can see here I am using an enumerate function there, and you can see there, enumerate of set of tokenized text. What is it doing? You have got your tokenized text that has got all the words inside your corpus. Set function, what does it do? It extracts unique tokens out of it, removes any repeated tokens that are present, and then you will enumerate on it to generate your indices. So that's how you got word to index. Whatever word and then index. You have to reverse it, obviously, to generate an index to word, because output will be index based. From that index, you have to search that word and predict that word. For that reason, you require to reverse it. So you will be doing your index to word using items method. Clear with it? Okay. After that, see, I'll repeat this for you. Word to index, this using enumerate method, it will create a dictionary where each unique word is mapped to a unique index. Why I am using unique as a word here? Because I have used there a set function. Okay. Now, the index starts, very important point. Okay. We are doing text pre-processing. Okay. Generally, you have seen whenever you will use an enumerate function, indexing will start from 0. But for text pre-processing, you make sure that the indexing starts from 1, but not from 0. Why? I'll give you the solution when I am creating the model. Right now, I don't want to confuse you. Remember at this point, we are giving the sequencing of tokens from 1, not from 0. Why? I will give you the answer. Okay. Now, go back and print your vocabulary size. How much is your vocabulary size? How much is the vocabulary size that you are dealing with? 4,950. Quite a big data. Yes? 4,950 words are unique words, not words, unique words are there inside your data. Okay, and you can see word to indexing is also giving proper result. It is just a small snip of that output. Extension, I could not capture it better. Okay, now, next is what? Convert this text into integers so that your machine could actually work with it. I am explaining you this by splitting your data. The very first thing that you have to do is how much input you will be giving for the machine. So that how much, if I am typing an entire sentence, in our last exercise also I told, context size. That context window is very important. So this context window here is sequence length that we are talking on. On how many words the machine model should be made. So given here sequence length as 5, machine will pick up 5 words to predict the next word. Although this is sequence to sequence model, means output will be a sequence of word, but it will predict one word at a time only. So it is like next word prediction only with a context window of 5. Understanding? So sequence length that we are giving here is 5. You can give whatever you like. I am giving here 5. Again what? I am supposed to take up my text, take 5 words at a time, 6th word will be output. So first set of input, 5 words, output will be 6th word. Then omit 1, slide through. From 2nd word to 6th word, how many again? 5 words will be taken, 7th word will be the output. Then 3rd to 7 words will be taken, 8th word will be the output. Like that you will create input-output pairs so that the machine can take input as 5 words of data, generate you an output which is a single word. Understanding?
Now processes start. You are supposed to create input-output pairs out of a vocabulary of 4095 words. What is the sequence length? What is the context window that you would be sliding for? Okay, so sequence length is 5. Again, initializing my input sequences labels. Okay, here, mind it, because my corpus was big, I chose to work with only the index of this word. Previous exercise mein we chose to work with vectors. It was a very few lines of sentences. I explained you how entire thing happened in depth. Here also vectors we will use, but at a later stage. For viewing purpose, I am viewing only indexes. Okay.
Now, I am creating input sequence list 1 and I'm initializing this list, output labels, input sequences. Now what I am supposed to do? I am supposed to generate these input sequences and output labels. So what is happening here? I am creating a for loop here. What is the range? Range is the context window that I am supposed to slide. Means what? After these first 5 sentences, then 2 to 6, then 3 to 7, then 4 to 8, that window. So how do I get that? Length of tokenized text minus the sequence length. So that will be the range for which you will be looping. Now, after that, what you will be doing for that for loop? You are creating input sequences by, the same thing. Okay, you are creating input sequences by appending every word to index token in that particular tokenized text for that sequence length. What is happening? You see, input sequences dot append. What are you appending? For again, you are beginning with a for loop. In that tokenized text, for that context window, you will be trying to append word to index to this particular input-output pair. So for that, what will happen? The very first token will be first token, index is 1, not 0. So first index word will be appended to my input sequence list. Then second, then third, then fourth, then fifth. Stop. Everything will be given in this. So this serves as one input pair. To that, what will be the output? Sixth. Are you clear? So 1, 2, 3, 4, 5 should go into my input sequence list. Sixth word index should go onto my output. So 1, 2, 3, 4, 5, 6 should be output. 2, 3, 4, 5, 6, 7 should be the output. Like this, the iteration should move on. And you generate an input and output pairs out of it. Now, you cannot directly work here without converting your x and y into tensors. So you are going to convert your input sequences and output labels into tensors. Important part, check the data type. What is the data type? Y. Both of them are integers. We are not chosen any vector form for our understanding here. Had I chosen vector, then I have to use their float. Okay? Because it's just an index. It's just an index. The location where that vector is. It is an integer. That's why long. Print the shape of input. Means out of 4,950 tokens, how many input-output pairs you have generated? How many? How many? 26,465 input-output pairs you have generated. Okay. So first 5 words, 6 is the output. 2, 3, 4, 5, 6, 7. Like that, combinations if you take pairs, input-output pairs are how many? 26,465. Y input has got the dimension as 26465, 5. Why it is 2D? Because input words are how many? Output value is only. That's why output there is one dimension tensor and input is a 2-dimension tensor. Now again, we will be using data loader. Till our last exercise, we were able to do this. Then we started building the model. We did not use data loader. Here we cannot do that. Why? Size of input dekho, 26,000 change. Huh? So it cannot read all those sentences at a time. You have to serve them into batches. Okay, otherwise what will happen? You can ask me, what will happen? Machine will not predict. I'll say machine will predict, but it will be very slow. There will not be any parallelism. It will be slow. Probably it may not give you proper accuracy because it will not be trained properly. I am not telling machine will not predict. Okay, so for better predictions, for better accuracy, for better generalization, better training, speed in the training, you will have to break down this into batches and give or train your model. Clear enough? For that, you must learn today data loader. Okay. So now, first what we are going to do is, you will be splitting your training set and test set by using this X and Y. Test size 0.2 means what? 20% of your data you will be using for testing, 80% of the data you will be using for training. What is that? Random state equal to 42? For every other machine, it will be able to generate the same results because it's a random generation. Na? Any machine can give you random results. So your model will be different every single time you are running it on different machines. So you have to give a seed for generation of that random sequences. Here the seed given is 42. Okay. Now, data loader. So you can see here, create a data loader object. See what is it? Data loader ka output will always be object. Okay? It will be object, that you have to remember. Creating data loader objects to efficiently handle batching for training and testing in PyTorch. Batch size you have to first frame in how much amount of batches you want your machine to get trained. So for all that input size of 26,000 change, you will be serving it in a batch size of 64. Okay, batch size here is 64, 2 power n format. Okay, here I am choosing it because it works better. So batch size here is 64. Train data set I am doing by applying this method. What is the method? Tensor data set. Taking input X train and Y train. So taking X train that you have splitted, Y train that you have splitted out of X and Y that you have generated, you are creating a train data set. That what does it do? It will wrap this X train and Y train into a data set and present it as your training data set. Okay. Similarly, you will go for a tensor data set here. You will be using X test, Y test, wrapping it and creating a test data set object. Clear enough? Now, you will see here what are we doing. You are using data loader. So try to understand. Data loader when you want to use, you have to first convert that into a tensor data set. So first tensor data set, then data loader. Now tensor data set ka train data set output you will be using in your data loader. Train data set, what is the batch size and shuffle equal to true. You will be applying it to data loader to create train loader, similarly test loader. What is the difference here between train loader operation and test loader operation? Figure it out. So why you have to give shuffle equal to true for training and not for testing? Because for testing you are only working with whether for a given input it is generating correct output or not. You are not bothered about on generalization part. That is done in training. That is the reason for training you have to keep shuffle equal to true so that it efficiently trains well and develop better generalization by shuffling of batches and samples throughout. Clear enough? Okay. So what you are doing, again I go back, try to understand. Decide how many batches you want to give to a machine. Before you convert that into a, pass it on through a data loader, you have to convert that into a data set. That is done through tensor data set method here. So first apply tensor data set to your X-train and Y-train, X-test and Y-test, generate training data set, generate testing data set. After that, give it to a data loader wherein you will pass how much batches you want to divide them into and give better generalization opportunity by keeping shuffle equal to true for training data set, and the same thing goes without shuffling for your test data set. Now, what it will do? It will create this. Suppose if I want, I am printing. Print train data set. What is this? What is getting printed? What is it? It's an object. Okay. So, what is happening here? The output, this output, when you print your train data set, it is just printing the location of the memory where this object is present. Okay, it is not a problem. It means that object is created. It's just that you are not able to view it. You are just able to view the memory location. You can ask me, ma'am, if I want to view, what should I do? So, you have to go and access it index wise. So, it is like print training data set of 1. Why 1, not 0? Indexing started from 1. So, train data set fun will print me now the first sample. So, look at the beauty. Now, you see these 5 set of sequence in your input, 5 words in your input of size tensor. If you give input, the machine should give the output as tensor 2327. So, like this, n number of input-output pairs you have created for your machine. So, given 5 words, what should be the next word? Given another 5 words, what should be the next word? Like that, you have converted everything into tensor and given as proper input and output to train your model. Now, I can say that, yes, my model is prepared. No, sorry, not model. Data is prepared to give in suitable input-output format. Here you have also divided your data into training data and testing data. Okay. Why you could ask me why you didn't do that in your previous exercise? I didn't do, na? Did I do? Text word prediction mein? Why? Data was very, very small. Okay, it will create an overfitting. Here the data is long enough so that I can train it on one data, test it on another data. Clear enough? Now, same goes with printing of test data set. You can, if you want to access, you are able to do. Okay. Now, total number of samples in testing and training, you can see, you can figure it out. Training data set, how many samples? 21,172. So, if there are 21,172 training samples, total number of samples, this is also training. Okay, testing, for testing you will have less because you are just giving 20% of data. Okay, that is again a repetition of training data set slide that has come. Okay, now what I am going to do? Yeah, what's wrong? So what we are going to do next? You got your input-output pairs. Now you can start beginning to actually define your model. My model's heart and soul here is attention mechanism. Okay, so we are quickly going to see how do we build that attention mechanism, for which you have to create and define a class. Okay, so here we define a class for scale.attention, okay, and wherein to the init function we are passing hidden size. What is this hidden size? Scale.productAttention uses what? Key, query, value. So this hidden state that I am giving over there is nothing but what? Key, query and value to calculate it further. Once you take inputs as queries, keys and values, what you will do? You will start writing a method called forward. What it will do? This particular method will start applying all the mathematical functions that we did in that particular formula. What was the formula for scale dot product? If you are using query and key, Q dot key transpose by under root dk. Dot product was Q dot k transpose. Under root dk was scaling factor. Correct or not? So here what we are doing, we are using matmul operation from Torch, and then we are passing input as Q comma K transpose, okay, and by NP dot sqrt self dot hidden state. Self dot hidden state will give me the dimension of my key. Okay, so you got here Q dot K transpose by under root dk being done. Okay, this will calculate me attention score. After I get my attention score, am I able to take it further? No. I have to pass this through a softmax function to get attention weights. So here you can see I am using torch.softmax. I am passing my attention scores that I have got it previously by applying dot product, and then I am choosing it here. Now here we convert raw attention scores into the probabilities, that we call it as attention distributor, and here we are also ensuring that each row of attention score sums to a 1. Okay. Now after that, what you are getting, you take the vectors of that particular key and multiply them, and you perform a linear transformation over them to get the final output. So what you are going to do, you are going to multiply these attention weights with respect to these values and store it inside an output. After that, the model, see, again I am explaining the same module. This module is taking 3 tensors, query, key and value. Query, what we want to find relevant information for. Key, reference for comparison. Value is the actual data. So you take query and key, find out dot product of it, scale that down to by dividing it by under root dimension of your key. Once you get that as an attention score, you pass that through a softmax function to get a probabilistic distribution. After that, every attention weight will be multiplied with its respective value or a vector. Okay. Now, output will be a weighted sum of all the values of V. Now, we are not doing this in this particular model, but there could be some possible improvements that you could do based on different applications that you will be doing in your future. What are they? You can also introduce padding. You can also introduce padding in your NLP task, wherein you introduce attention mask. That means the few things you can ask your model to ignore. Okay, few words you can ask your model to ignore. Attention mask, removal of certain words you can do in your NLP application. We are not using in your model, but there is a scope of improvement. You can suppose sometimes it so happens that your training accuracy is high and testing accuracy is low. That means your model can be overfitted. Whenever the model is overfitted, you can go for regularization techniques. One of them is to introduce a dropout layer. That you could do. Also, you can be able to use multi-headed attention extension, which we are not using in our model. So, few improvements are there that you can work on based on application to application throughout this particular part that I have explained. That means while building your attention class, these improvements could be done. Now, we will define an auto-completion model, but then we will take a small break, and then after the break, we will start working on building our model. Till now, what we have seen was pre-processing of your data, building attention for your model. Now, we will see how to build our actual model with attention. We had our input as a text file, which had got a vocabulary of around 4,950, let's say, words were there, unique words were there. When we tokenized and we checked the vocabulary, there were around 4,950, 4,000 change words were present in your vocabulary. Okay. Now, you indexed each and every token, but the words cannot be directly fed into model. You had to pre-process that particular tokens. How? Based on how many words you are taking together to form a context vector. What is your context window? So the context window for this model, we chose sequence length as 5. So we divided our input into a data set which should have 5 tensors, as you know, it should be in tensor format. It should have 5 words in the input. It should have 1 word at the output. What should be the next word for prediction? So we wanted to figure out a way so that we break down our data as a set of input-output pairs, right? So for that, what did we do? We calculated vocabulary. We did word to index, index to word. Post that, we used test train split and we applied a splitting over onto that particular data, wherein 80% of the data we will be using for training, 20% we used it for testing. Just not splitting, you have to convert that training set into a suitable format which can be processed by the machine. So for that reason, we wanted to use a data loader. How to use a data loader? Directly you cannot. First, you have to convert it into a tensor data set, okay? And that tensor data set you create for both training as well as for testing. And then that tensor data set you will be using in a data loader method. So when you do that, you create 2 objects. One will be for training, another will be for testing for your data set. You cannot directly access it. You have to do the accessing through indexing to check for 5 sequence of words as tensor, what is the output tensor that is present. So you all saw that part, and input was ready enough, fair enough to be applied to a model. Then you went ahead and you wanted to begin your model. In this particular sequential model that I want to build, I wanted to impart attention also. For that, I first defined a class of attention wherein I am using scaled dot product mathematical operation using self-attention. For that, you all know I require query, key and value. Alright, use query, key, value of self-attention and apply mathematical function of scale dot product attention. Okay, so scale dot product attention, how does it work? It works by first figuring out dot product of query and key. Okay, and then you try to scale it down with square root of dimension of your key. Once you are done with that, you create an attention score out of it. That attention score, you cannot use it directly. You have to pass it through a probabilistic distribution function like a softmax function. Once you are done with that, you will multiply each attention weight that you get. Attention score when passed through softmax become attention weight. Now each attention weight will be multiplied with its respective value. After that, weighted sum of values will be your output from your attention class. Clear enough? Now this attention class, we will be trying to call it in our model. Okay, so first, are you clear with what all steps that we have done? Now, what are these QKV? By the way, QKV are nothing but the hidden states that you will get from your model. That will serve as your QKV. We'll use that in the model, you will understand. So now once you have done with that, we will now define our model. The name of my model here, I named it as an auto-completion model because my aim is that if I give it 5 words of input sequence, it should be able to auto-complete it for the next 10 words also. Understanding? So that is my aim from this particular model. What is the aim? If I give 5 words of input sequence, it should predict or auto-complete the next 10 words in sequence with respect to the novel that I have given it. Clear enough? That's how the name I kept for this model is a auto-completion model. It will be a sequence to sequence model because it is taking 5 words of input sequence, generating 10 words of output sequence. Don't get confused. It will be generating 1 word at a time only. But it will give you output as a sequence of those words, one after another. Prediction will be 1 word at a time. Sequence will be generated and given as an output. Clear enough? So that's how it is a sequence to sequence model with attention. What type of attention we have created for it? Scale dot product attention using self-attention. Scale dot product attention mechanism using self-attention. Break it down. Mathematical operation between query and key will be scale dot product, and key will be created out of the tokens of same batch. That's how self-attention. Clear enough? Okay. Now, apart from attention, you are performing processing on sequential data. So, what type of neural network you will be building here? Either RNN or LSTM or GRU. Here I am preferring LSTM because I already taught you LSTM. So here we will be using an LSTM model and embedding layer. Very important. This is a new type of strategy that you will be learning to play with vectors. You remember my exercise of predicting next word? What did I do? I randomly generated my own vectors. That's how I was able to display you with vectors in the initial stage only. That was one of the ways. See, everybody has got their own style of coding. At that time, I took that style of coding wherein the data was very small and I thought I could produce the vectors from randomly generated thing and I could show you also, display you also. So that was that style of coding. Then in the exercise where you did, you tried to work with pre-trained vector models. What did you use there? Word2Vec. So that was one way of using your vector into your model. Today I will teach you third way of how you can convert a word into vector using PyTorch. Okay, it's most simplest. That's the reason I first started with generating random vectors, how actually vectors will be. Then use a pre-trained model. Now I will teach you how to use an embedding layer. Are you clear? So what all are requirements of your model now? You require an embedding layer. You require to incorporate LSTM layer mechanism inside it. You require an attention inside it, which is scale dot product attention. Also, for the latter part of classification or prediction, you will be using a fully connected layer. Are you clear? So these are all things you have to now write code for building a particular model. You already created a class for attention that you will instantiate in your model. Okay, now let's see. So I want to first create another class called as auto completion model. This is how the code looks like. I'll break it down and I'll explain it to you. So you can see in that class called auto completion model, I'm having an init function for instantiation, and the parameters that I am passing here, can you see how many parameters are there for our model here? Basic parameters, self to rahega. 3. What are they? Vocab size, embedding dimension and hidden sign. So vocab size is nothing but what is the number of tokens that you have got inside your model, and then embedding dimension. When you are converting a word into vector, till now in this process did we use vectors anywhere? We are working with indices only, no? Now, when we are building model, we will actually work with vectors, because eventually machine will not understand words. It will understand only numbers, vectors associated with that particular word. So now what you require is, you have to set the dimension of the vectors for which you want to, for which you want your tokens to be converted into. Okay, so vector dimension is important. That is here embedding dimension. Next is hidden state. But of course, when you have got your
hidden state, it will always be in the part of 2 power, in the form of 2 power n, 32, 64, 128, like that. So now, what I am doing here is, vocab size is the number of unique tokens that you have got in your vocabulary. Embedding dimension is dimensionality of word embeddings, means every word should be converted into what dimension of vector. Next is hidden size, number of units that you will be using for your LSTM and attention mechanism. And attention mechanism because outputs of LSTM will be hidden states, and those hidden states are only serving as query key and value for your attention mechanism. That's why hidden states will be valid for both LSTM as well as for attention mechanism. Okay. After that, you can see very easily I am creating an embedding layer. What am I doing? I am calling this method called embedding. I am passing parameter as my tokens, and what should be my embedding dimension?
Embedding dimension is 100. Then every token in my vocabulary will be converted into a vector of size 100 very simply without using any scratch random generation through this layer that I am calling here called as embedding layer. How it will do, ma'am? Inside the embedding layer is also one neural network which is already pre-trained. It is pre-trained with some pre-trained vectors like word to vec or globe inside it. All you are giving it, that black box, is some words and dimension. It will do the work for you and generate you with your vectors. How? Pre-trained vectors only. You are not selecting. You are calling embedding layer, it is doing. Generally, it is word to vec only inside it. Are you clear? So, this entire thing is the beauty of your PyTorch library. Okay, simply calling that layer, giving the inputs and getting output out of it, you recollect back your first 2 codes, you have done everything from scratch. So entire that processing part, that writing part is gone. You are just simply doing those many lines of code in that one line of code wherein you are calling an embedding layer, passing on tokens, passing on dimension, getting output out of it. So this is third way of using and generating the vectors inside your model. How? By calling a embedding layer. So it will convert all your input word indexes that you have got into dense vectors equivalent to the size that you choose. Here the size is defined by embedding dim. Helps the model learn meaningful representations of the word. Now, once you got your vectors, what you have to do? You have to pass those vectors to your sequential model using LSTM. So, I am calling their LSTM layer, and to that LSTM layer, I am giving how many parameters? 3 parameters. One is the embedding size. What is the size of the vector that I am going to provide to? What is the hidden size that I am expecting out of my LSTM? It should be always in the power of 2 power n. And then batch first equal to 2. To true? Then what effect it will have? Whenever I write batch first equal to true, what effect will it have? Very good. It will change the dimension of my inputs and outputs. To the existing dimension, the first it will be prefixed with its batch number. So it will be batch by whatever be the dimension of your input. So changes the dimension of your input and output. So this is what we are doing in LSTM. We have to send how much size of vectors you are giving to it for processing, how many hidden states you are going to expect out of it, and also you are changing dimensionality of your input and output, for which batch first equal to true, because everything you are working in terms of batches. Okay. How many batches you are using in this model? 64. We already discussed it, right? Now, Now what will happen? Once you get hidden states from your LSTM, so LSTM ka what you are getting hidden states. These hidden states earlier we used for direct prediction in our previous exercises. Now we will not. These hidden states will be used and given to attention mechanism to save time and run parallelly everything. Okay, so hidden states will be given to the, you can see, hidden size is given here to the scale dot attention, and then LSTM output serves as a query, key and value to your scale dot attention method. What is this? This part that we have written. Okay, I'm going back. This one. Okay, we read this, right? We wrote this, scaled dot attention. We are calling this over there. We are instantiating this class in our model. So what does this class say? This particular has got, this class has got two methods inside it, I think. One is where it is invoking the hidden size. Hidden size is nothing but hidden state out of your LSTM now. And also it is using the same hidden states as Q, K and V to calculate attention weights. So now going back to your model, look at here, I am using the same thing, I am passing this as hidden size. So whatever hidden size you are choosing for LSTM, the same you will be passing it over here, and the output of LSTM serves as QKV for your attention. Now we'll see how do we use it. Next is what? You require the attention output to map to a vector of vocabulary size, telling what is the probability of the next word. For that you require a linear transformation which is achieved through a fully connected layer. So are you clear? What are you doing here? You are calling an embedding layer. Sit down both of you. You are calling an embedding layer, then you are calling an LSTM layer, then you are calling your attention layer through your class that you have defined, and then you are calling your fully connected layer. So this layer by layer now you have designed your model. Now actually we will see what is happening inside it. So in this particular thing, what is happening? Self dot embedding, output of embedding layer mein you are now applying your inputs that you are giving. So self dot embedding is the output of embedding layer, right? What are you doing there? In this, it will convert the input token indices X into vectors stored inside embedded. So indices of the words will be converted into vectors. Previously, we were doing it in beginning of the code only. Now we are doing it while we are designing our model. Okay. So every token will be converted into a vector. Then what you are going to do? You are using your LSTM output. You are using these vectors inside your LSTM layer. Once you get that, you obtain output. What is the output of LSTM layer? There are two outputs. Here I have mentioned LSTM out, comma, underscore. Why underscore? To ignore if I am not using something. What I am ignoring? Cell state. What I am taking? All the hidden states. Okay. So LSTM out I am taking, and this hidden state, which is my output hidden state out of LSTM, will be taken into my self-attention part as query, key and value. Three of them the same. That's the reason those three parameters are hidden state and hidden state. Okay, so LSTM out and LSTM out serves as query, key, value given to the attention layer and getting attention out of it. And then what you are going to do, it applies self-attention only onto the last hidden state. Okay, you are going to use a last hidden state out of it, I'm sorry. So, you are going to have here attention out, you can see colon -1 colon because you are only taking last hidden state out of it, and focusing on important words using self-attention over here. Now, after that, it is passed through fully connected layer to produce your logits. Okay, that you will be working. Logit are your rough vectors that are produced at the end of your model. Okay. Are you clear with this particular part of model building? Very important. Okay, layer by layer, you first created embedded layer, then LSTM layer, then attention layer, then fully connected layer. Output that would be produced will be your output logits. Logit means rough calculations of your vectors. Okay, now after that, what will be the output logit? It will be prediction for the next words. Matlab, for all the words that are present inside your tokens, it will give rough figures. What could be the probability? You have to pick up any one word and do. So that processing again we have to do. Okay. So let's first try to complete our model by instantiating it by choosing suitable loss function and suitable optimizer. So here vocabulary size is length of word to index plus 1. Why? Because we started indexing from 1. Again, I did not give you that answer. Why 1? I'll give. I remember that. Okay. Now, choose your embedding dimension. I have chosen here 100. Choose your hidden size as 2 power n because the corpus is big. I am trying to choose this as 128. Okay. Now, again these are user specific. You can change them based on your application and results. Now, I am instantiating my model called auto completion model, giving my vocabulary size 100 as my embedding dimension and hidden size as 128. I am applying a loss function since I am supposed to choose one word out of multiple words. It is multi-category classification. For that, loss function will be cross entropy loss and I am saving that into criterion. Also, I am supposed to choose optimizer. The best choice would be to go for Adam. We have already seen what are the advantages of Adam optimizers. Okay, it provides momentum while we are converging to minimum gradients. That's the reason we go for Adam in most of our neural network models. So you can see I'm applying Adam to my by passing through my model parameters, and then the learning rate I am beginning is with 0.01. Again, it is user specific. It's a hyperparameter that you'll have to work on. Okay. So, learning rate I have kept here LR equal to 0.001 and I'm applying my optimizer, saving results into optimizer. Now, train the model. I'll again break down this for you. So, how do I train this particular model, guys? For training this model, I'm supposed to pass parameter as what model that I have written. Train loader. Again, train loader came into picture. Train loader is what? Data that you have converted it into training data set, testing data set. Training data set mein X-train, Y-train. That we converted through data loader as a data set, as an object. Yeah. So here that train loader, validation loader is your test set. You splitted that and converted that into two objects, training object and testing object. That you will be passing here. You will also have to fix certain number of epochs, which is again user specific. Okay. Now, after that, for every epoch, you are supposed to train this particular model. Initially,
it's supposed to be calculated. At the end, we are going to take average of all the losses that I have got for that cycle. So I am taking a total loss as 0. Now, for all the inputs and labels that are present in my training data set, I will apply inputs to my model, save it into output. I already have my outputs present inside it. Difference I am going to check for the loss using cross entropy loss function, and then I am going to apply optimizer dot zero grad, wherein I don't want to store or accumulate any gradients and waste any memory. So optimizer dot zero grad, and I am applying backward propagation to update the weights and other parameters of my model. If you want to do it at every step, optimization, then you have to go for optimizer dot step. Okay, therein you created your good forward path and backward path to obtain optimized result, calculate the overall loss and append it to the total loss. Once you get your total loss, you divide it with the total length of your training data set to get an average loss. What I am going to print here is an average loss. Okay.
So for every epoch, I'll be printing my average loss. Now this I have created a train model method. Now also I require validation. For that I have to evaluate my model, and I will be doing here evaluation with no gradient calculation, because testing phase pe you don't require that back propagation part, you don't require gradient calculations. That is the reason here no grad I am going to use, torch.nograd, and I am going to pass all my inputs to the model and check what is the output that I am getting. Now let's apply that to our model. Here I am using train model function which I just wrote, pass on train loader, test loader, which are my training and testing data sets that I created using data loader. I am setting number of epochs as 100. It is again user specific. Based on the epochs also, there will be change in the amount of loss that has been calculated. Okay, so now you can see here, you have begun with the first epoch with a loss of about, average loss of about 7.08. As you begin, it was 7.08. As you end up with your 100th epoch, the loss came down to 0.01. So you could see with an increase with the number of epochs, average loss started diminishing to a negligent of 0.01. That means whatever we have created is a good model. You may find accurate results whenever you are calculating your output. Now, यहाँ पे model building stops. We still have to write one more function for prediction. Prediction means to see with our own self whether the output is correct or not. यहाँ पे you are getting internal details, like internally there is no loss. So let us actually check if it is going to predict you with correct result or not. Two ways of doing. One is interactive prediction, which I already taught you in the previous exercise. Interactive prediction mein you should be very cautious how much words the input should be given. Suppose I gave 2, then it should raise me a value error telling minimum 5 words you have to enter. If I give 10, then you have to truncate it to 5 as your context window and work with the model. Obviously, we designed our model with 5 words. Okay? Otherwise, it is able to predict you the result. Here, I did not use that. I have chosen a very simple way of prediction because the code already became long enough. You can improvise this particular code on your own. So now I am going to write a function for auto completion called as complete text 1. So this function is taking parameter as the model that I designed. What is the start text? Start text means the 5 input words that the user will give to the machine. Okay? And word to index, index to word, the vocabulary that we have created in the starting. Why? Because it has to look up to that particular word after prediction and produce you the result onto your screen. And then max length. Max length is equal to 10 means how many next word in a sequence it is going to produce. So I chose this as 10 because I already told you when you give 5 input, I want to create an autocomplete model that could autocomplete the next 10 words coming in the sequence. So this max length is the next how many words you want to get it printed into sequence. Evaluate your model. Now, as the user gives the input, machine has to read it. So again, you will have to tokenize what the user has given and then start working. So what you will do here, as the user gives the start text, okay, the 5 words that the user inputs, it has to tokenize, it has to get index out of that particular token, it will have to convert those indices into tensors. Now the machine will understand what 5 words are given as an input. So given an input, make it suitable for the machine to read it and then incorporate in your model so that it can predict for you. Okay? So for that, tokenize, convert it into index and then into tensors. Okay? Next, after that, what you will do, you will start your model over there that will generate your prediction. You will give the start text, that is your text that you want to give it as a prompt for generating your output. Word to index, which will map the word to their indices. Index to word, which will map back. Index to word we will use in generating output. Word to index you will use in taking the input. And then maximum length, as what I told, it will control how long your auto completion would be. Now, I think I already taught you this. Now, after you tokenize this, you will look up to the index of each word, important part. I asked you, the indexing begins with 1. है ना? Why? This method you check. See here, what am I doing? Token indices is equal to word to index dot get token comma 0 for tokens in the token. Now, word to index get token comma 0, what it will do is, input sentence I got as a machine, I tokenized it. For every token, I will look up into my word to index dictionary and check for its index value. Yes or no? If I did not find any word, then automatically I'll generate that token as 0. So now do you remember why did I tell you? You start your indexing with 1 for your input words. Why? Because whenever there is some new word which is not there in your vocabulary, automatically it will tokenize it to 0. That's why tokenizing began with an index of 1 for our inputs. Okay, so now you have input token 0 also here. 0 for some unknown word, 1 to so on up till your last token for all the sequences that you have got. Clear enough? You have to please understand this part. There will be some time that a word given by a user will not be there in the data that you have got. If certain words get encountered like that, automatically when it looks up, it cannot find that word. So it will generate a token as 0. Okay. Now, if the word is not found, it returns a 0. This is also called as a padding token. So you see here now, what are we doing? We have using a padding token to just see if a word is present in the word to index list or not. And then once you get that, what are you going to do? What are you going to do? You are tensorizing that particular index, and then for that you are starting to run your model on those input tensors. Once you have started to run, how long you are going to run? When you run it once, it produces one word as an output. So how much should be the looping for? When you run your model once, and a word will be predicted once. But auto-completion model requires how many such words in the sequence? So you have to for loop your model there for how many words you want to auto-complete. Are you understanding? For that reason, you can see here, for in the range max length, this underscore means I am not using any variable to name that loop, thing where I am rooting, like it's for I. Okay, so here it is for underscore in range of max length. Max length is how many words you want to auto complete. For that many words, you will be running your model in a loop. So with no grad again, with no grad, torch.nograd, because it's my prediction, my testing. Testing mein you will not calculate gradients, unnecessary wastage of memory, wastage of time to compute gradients. That's the reason to avoid that. With torch.nograd, you calculate the output using the model for these tokens, token tensors. Okay, and then what are you going to do? You are going to predict. What is it? Predicted index is equal to output dot argmax1 dot item. Very important. I told you when I build the model at the end कि every word को there will be a logit associated. So which word will you take as output? Model में, output में you will get logits associated with all the words. So यहाँ पर ना you will be using this part. This argmax of 1. So output logits में which is having more close, which is more close towards 1, that has got highest probability, that word will be printed. Are you clear? So this is important, guys. Predicted index is nothing but output dot argmax1 dot item. Dot item will give me the index of that particular word. So for all the words you will have logits generated in as an output from model. Here to all the logits you will do an argmax. You will see which vector is having its value more closer to 1. That is got highest probability. To that you apply dot item, means that vector has got what index now you fetch. Now what you will get as an output? The index of the word that you want to go with. How is that word predicted? Using LSTM and attention mechanism. Are you clear? Now what you have got? Index associated with what should be your next word. Now what you will do is, you will choose the auto completion hai na? It will be a completed sequence. So completed sequence will be previous word plus space and then follow it up with the next iteration result. So like that, how much sequences you will get? 10 words in a sequence, because you are iterating your model 10 times. Okay, so that's what you will get. After that, what you will do is update the token tensor. ये भी करना है ना. Model में you have got the output once. You have to update your input again. So you are going to update the token tensor to include your next word. Okay, token tensor फिर से डाला and then repeated with your model and got your output for the next thing. So you will return the completed text here. You can see you have got output as only index. You still did not get the word. So you will do what? Do index to word mapping again to get back your word. So you can see here, this is your testing, that is your output, how does it look like. So here I am giving from the novel itself 5, from an entire 4095 words. कहाँ से तो भी I am giving these 5 words and it is predicting me correct auto completion. Okay, so suddenly she came upon a, when I gave and I applied it to my model here and I gave max length 20. You can change it. You can predict next 10 words or 20 words based on your requirements. So here I gave 20. So you can see suddenly she came upon a little 3-leg table, all made of solid glass. There was nothing on one listening. So entire thing is getting predicted. And when I cross-verified it, it was the same sentence from the novel. Okay. So from your data, when you are giving only 5 words, you are able to predict upcoming n number of words and auto-complete that sentence. Can be 10 words, can be 20 words, can be 30 words. Agar prediction of one word you are able to do correctly, remaining producing sequence is not a problem. Are you clear, guys? What did we do? There were some other samples also that I checked and I was getting correct results only with this particular model. So here the strategy was take input as a text file. Here I have taken, you can take CSV files also, and then provide suitable pre-processing wherein you will convert that text data as a standard set of input and output in tensored formed objects using data loader. Use data loader, use tensor data set and get your proper samples of training and testing. Here we are giving 5 words as a sequence. So input will be a tensor of 5 and then 5 as its size, and output will be of size 1. Once you have got your preprocessed data, start building on your attention mechanism. Here we have chosen self-attention, so you will be having query, key and value. How you will be obtaining your attention score depends again on another mechanism here, which is scaled dot product attention mechanism. You use that and calculate attention scores. Attention scores will not be sufficient. You require probability, so pass that through a distribution function like a softmax function, multiply it with its values, that is your vectors, and then get a weighted sum which should be able to get you what should be the next word in attention. Once you get that, you start building your model. These two were your starting part. Once I started building the model, obviously what I first do was to convert all my words or unique tokens into embeddings, word embeddings. I did that in this model through embedding layer. Okay, so embedding layer mein I have to fix a particular dimension of my vector that I want my words to be converted into. I get those vectors, I pass those vectors through LSTM layer, I get hidden states. Hidden states will be given as Q, K, V to my attention mechanism. I get my attention output. I only consider last hidden state to calculate my next word into the prediction. This was all about my model, and then I start instantiating my model. I start fixing my loss function as cross entropy. I want to get an optimized result for which I am getting Adam. Use 0 grad and no grad, 0 grad while training, no grad while testing, all those things you must remember. Build a particular model, evaluate that particular model on your validation data set also. Pass on suitable information and get the result. Mind it, result will be logits associated with every weight. Result will not be direct prediction. Result out of LSTM will be logits associated with every weight. So when you are doing prediction function, you make sure you argmax those logits, round off to them in the probabilistic range of 0 to 1. The one with a maximum nearest to 1 will be pulled out. You will be getting an index of it if you place an item function, dot item function to it, dot item method to it. It will give you the result as index of that word. Then suitably write a method, how many such indexes of the word followed by spaces, how many amount of time, 10 input words, 10 output words, 20 output words, like that. So that will be a looping part. Then what you will do is, do a index to word mapping. Index to word mapping mein it is important that you do a padding token. For that reason, whenever you designed your model, word to index mein you started with a sequence length of 1, not with 0, because at the end mein, when you are doing index to word mapping, you have to make sure that when the user gives input, if some unknown word is there, out of context word is there, it should be given as a token 0. Are you understanding this? So this all process is done, but then when the user is asked to give an input sequence, again you have to pass through tokenize operation, understand that, convert those words into its index, and those tensors, indices tensors, you have to pass through your model, get the prediction out of it. Prediction will again be the position of your output word. You will convert it back into your actual word, and let's say based on the looping and how much times the looping is, that many number of words will be produced in the output. So here in auto completion model, I have given 20 words auto completion. So 20 times the model will be iterating to produce next words. See, this is next words. That's why you have to make sure in the model you have to change your token for the prediction of next word, so that in sequence next words will be predicted while calling your model 20 times. Are you clear with this? Yes or no? Yeah, so this was all about designing an auto completion model. Auto completion model is nothing but word prediction only. I'm naming it as auto completion because you can predict it for, auto complete it for so many words. Okay, so this is an auto completion model that I have designed using attention mechanism, using LSTM. Ma'am, can you design this auto completion model only with LSTM? I'll say yes, why not? But then if I use attention, time taken to get the output will be less. Moreover, accuracy will also be better. Okay, because I have to go through na. But here what I am doing, data loader use kara hai, everything I have used, that means proper training hai, proper generalization hai. It will affect accuracy of my model. Are you understanding? If you go through this way. Can I do it with my traditional LSTM? Yes, you can. Time taken will be a lot of time will be taken to train your model and get output. Are you clear with this? So, by this, we finish attention mechanism. Tomorrow, you will do a hands-on session on the same attention mechanism and LSTM exercise with some different expectancies. And then later, you will be starting with transformers, which will be taken again by Asha ma'am. Okay. Any doubts so far for this session? Okay. So quickly, I'll start up quiz for today. You have to answer. Okay.